Dream to become the next Sir Isaac Newton or Albert Einstein? Learn calculus from Refath Bari, aka 800/800 guy, is teaching calculus this year. Watch his videos.
Hello folks, what's up? Finally we're starting calculus today, and the first topic we're doing is limits. So today we're going to introduce the concept of limits with something you're already familiar with, finding the slope of line. So if I give you a line, let's say I give you y equals x, right? The standard line. It has a slope of 1, it has a y-intercept of 0. And if I tell you to find the slope of this line using any 2 points, how do you find the slope? Well, let's take a look. Let's say this first point has an x value of x. Second point is a little bit farther than the first one, so x plus h. Right, so far so good. And let's say the name of this function is f of x. Right, so the x-axis is this one. Okay, so what is the coordinate of this first point? The first point has a coordinate of x, and if we plug this x into the function, we'll get f of x. Same concept with f of x plus h. So the coordinates of our second point is x plus h, comma f of x plus h. Okay, good. So now we have a general idea of what our 2 points are. Now how do we use these 2 points to find the slope of this line? Well, as you all know, the slope, or m, is given by the change in y over the change in x. Right? What is the change in y here? Well, it might look a little bit more obvious if I made a triangle out of this. The change in y, if you can see more clearly, is f of x plus h minus f of x. Right? This has a y coordinate of this, f of x plus h, and this point has a y coordinate of f of x. So their difference will be f of x plus h minus f of x. So that's what our numerator is going to be. Okay, how about x? That seems much easier. The distance between these 2 points is simply going to be, right? If we simplify, okay, good. So this looks kind of different from your standard y2 minus y1 over x2 minus x1, but the concept is the same. And the reason why I give these abstract notations is because we can use this and apply it to finding the slope of a curve. Let me show you what I mean. So instead of finding the slope of a straight line, let's say you're asked to find the slope of something curved, such as this function. Let's say it's your standard x squared, right? Second degree polynomial. So if someone tells you, if someone asks you, hey, what's the slope of the tangent to this polynomial at this point? Well, what are you going to say? Well, you can't use the same slope formula because this is a curved line. So what you're going to try to do is make an approximation. And this is how we do approximations and limits. So let's say I pick 2 points that are that surround the point we want to find the tangent to. So let's say I have this point and this point, right? I'm going to apply the same method as I did here. Right? Let's call the x coordinate of this point x. This point will have an x coordinate of x plus h. X plus h is simply a x coordinate that's just a bit bigger than x, arbitrarily bigger. And let's call this function f of x. Same thing. Once again, the coordinates will be the same. It's going to be x comma f of x. And the coordinate of this point is going to be x plus h comma f of x plus h, right? So far so good. So when we apply this formula, the slope formula here, what are we going to get? We're going to get this exact same thing, right? So what's the point of using it to find the slope of the tangent if we want to find the slope of the tangent at this point? Well, the reason why we do it is because it gives us an approximation, right? If we find the slope of the line using these 2 points, and then we shorten the distance between x and x plus h, we're slowly going to approach the slope of the tangent line. Let me show you what I mean more clearly. So let's say this is the graph of x squared, right? Okay, these are the 2 points we're finding the slope between. Right, and this is the point, this is the tangent line that I want to find the slope of. As I bring the distance between these 2 points closer and closer, this secant line here is going to slowly approach the slope of this tangent line. And that's our goal, to make this distance between x and x plus h approach 0, so that the slope of the secant line can approach the slope of the tangent line. So how do we express that in notation? Well, we take this and we add limits to it. Let me show you what I mean. So, okay, so let's say the limit as h approaches 0. You might be thinking, why do I have to make h approach 0? Because remember, h is the denominator. H is what you want to decrease so that the slope of the secant approaches the slope of the tangent. So that's why we have limit of as h approaches 0 of f of x. And of course, this is what the derivative of this function is going to equal, f prime of x. And this is going to equal, our standard slope formula, which we had right here. F of x plus h minus f of x over x plus h minus x. Well, as you can see, you can simplify that down to h. Now comes the easy part, right? This is just, it boils down to algebra. So I have the limit as h approaches 0 of f of x is equal to, remember, what was our original curved function? Y equals x squared. So I take the input, I square it, x plus h squared. Same thing with this one. Oh, sorry, plus, minus. Okay, let's just do some simplifying. Let's see what we get. As you can see, minus x squared, positive x squared. Boom. Now we're left with what? We're left with the limit as h approaches 0 of f of x is equal to 2xh plus h squared over h. Now you can factor out the h on the top, and what will you get? If I factor out the h on the numerator, I will get the following: h 2x plus h. Now, as you can see, boom boom, numerator and denominator cancels out. I don't have any more space left, so I'm going to simplify on this line. So as you can see, I'm just left with 2x plus h, right? Now, you're probably thinking, okay, I simplified as much as I can. What do I have left? Well, let's take a look at what we're doing. We're making h approach 0. We're making this distance between point A and point B approach 0. Now, as h approaches 0, even though it'll never actually be 0, this quantity becomes infinitesimally small. It becomes insignificant. We can just disregard it. We can just pretend it's 0, even though it never actually becomes 0. And so, the derivative of our original function, x squared, is equal to the limit as h approaches 0 of f of x. And that turns out to be 2x. Okay folks, so that was just an introduction to the topic of limits. Next time we're going to be doing the epsilon delta definition of limits. And yeah, I hope to see you next time.
Bari Science Lab to fall in love with math and science, especially programming.